Welcome back. Let's learn about finding the angle between two vectors. Alright, so in Calculus 3, sometimes we're going to be interested in knowing the angle between two vectors. But in order to understand how we find that angle, we need to recall something from trigonometry. In particular, I'm talking about the law of cosines. Now you may or may not remember this, that's totally fine. I'm going to tell you what it is in just a little bit. But first, if you take a look at this triangle here, the capital letters A, B, and C represent the three angles of this triangle. This is angle A, this is angle B, and this is angle C. And then across from each of those angles, we have a side length. Across from angle A, we have a side length represented by lowercase a. Across from angle B, we have a side length represented by lowercase b. And then across from angle C, we have the side length represented by lowercase c. Okay, so for this triangle, the uppercase letters represent the angles, and the lowercase letters represent the side lengths. And for a triangle like this, what we can use the law of cosines for is find an unknown angle of the triangle given that we know the three side lengths. Right, so for example, let's say that we wanted to find angle A, the angle between side length B and side length C. We can find that angle using the law of cosines, which says this. It says that lowercase a squared is equal to lowercase b squared plus lowercase c squared minus 2 times lowercase b times lowercase c times cosine of angle A. All right, so this equation right here is a result of the law of cosines, and we can use this to find angle A. All we would have to do is solve for A in this equation. But as you can see, this equation is defined with lowercase a, b, and c, and so we need to know what those side lengths are of this triangle in order to solve for that unknown angle. Okay, so that's our little refresher on the law of cosines, and so keeping this in mind, how do we apply this to finding the angle between two vectors, right? If we have vector v and vector u, how do we find the angle between them using the law of cosines? How are these two things related? Well, what we can do is form a triangle with these two vectors. You can kind of already see that we have 2/3 of a triangle here, right? Vector v would be one side and vector u would be another side, and then we could have a third side that would connect vector u to vector v, and we would want to represent that side with another vector. And so I'll do that here. I'm going to draw a vector connecting vector u to vector v, and we currently don't know what that vector is, so I'll represent that with a question mark, but we can figure out what it is equal to using what we know about vector addition graphically, right? You can kind of see here that vector v would be the resultant vector of adding vector u and this mystery vector. Remember that when you add two vectors together graphically, you take the first vector and then draw the second vector starting at the terminal point of that first vector, right? So we have vector u, and then we're drawing this mystery vector starting where vector u ends. And then the result of adding those two vectors together would be the vector that starts where vector u starts and ends where that second vector ends. And so that would be vector v. And so if we were to represent that algebraically, we would have vector v is equal to vector u plus the mystery vector, right? We're saying that vector u plus this vector is going to be equal to vector v. And so if we wanted to solve for that unknown vector, what we can do is subtract vector u from both sides of the equation, and that will give us that vector v minus vector u is equal to that mystery vector. All right, so that vector that we don't know is actually equal to vector v minus vector u. And so I'll relabel that here. This is vector v minus vector u. Okay, and so now we have a triangle formed by three vectors. And so we are going to be able to use the law of cosines for this triangle to find this unknown angle. All right, but now remember, when we use the law of cosines, in particular this equation right here, that's going to allow us to solve for angle A, we need to know the side lengths of this triangle, lowercase a, lowercase b, and lowercase c. If you look at our triangle here that involves our three vectors, we currently don't know the lengths of the sides of this triangle, right? As of right now, we're just representing each of these sides with a vector. But remember, the length of a vector, or the length of the sides of this triangle, would be represented by the magnitude of each of these vectors, right? The magnitude of a vector is its length. So the magnitude of vector v would represent the length of this side of the triangle, the magnitude of vector u would represent the length of this side, and the magnitude of vector v minus vector u would represent the length of this side. So if I redraw our triangle here, it's going to look something like this. This is the angle that we're trying to find, the angle between vector v and vector u. This side length is the magnitude of vector v, this side length is the magnitude of vector u, and this side length is the magnitude of vector v minus vector u. All right, and so now that we have a triangle with an unknown angle, but 3 known side lengths, we can set up an equation using the law of cosines that will allow us to solve for this angle. All right, so let's apply this equation right here for this triangle to this triangle. In this case, this angle theta is going to correspond to angle A. So in this equation, the first thing that we start off with is a squared, where lowercase a is the length of the side that is across from angle A. So for this triangle, we're looking for the side length that is across from angle theta. That would be this side length right here. So our equation is going to start off like this. We're going to have the magnitude of vector v minus vector u squared. And that's going to be equal to the rest of this equation, but applied to this triangle here. Now the next thing we have is b squared, which is this side length squared. In the case of our triangle, that's going to correspond to the magnitude of vector u. So we'll have the magnitude of vector u squared, and then we're going to add that to c squared, where c represents the other side length of the triangle. So that's going to be the magnitude of vector v. So we'll have the magnitude of vector v squared, and then we're going to subtract 2, right, minus 2 times b times c. So now we're going to multiply by both of those magnitudes again, but they're not squared this time. So we'll have the magnitude of vector u and the magnitude of vector v. Now I'm running out of space here, but after that, what we're going to do is multiply by cosine of the angle we want to find, which in this case is theta. So we'll have cosine theta. Okay, and so now we have an equation that will allow us to solve for this angle, which is the angle between vector v and vector u. The law of cosines allowed us to form this equation. Now all we have to do is actually solve for theta. All right, and so let's work on that. Let's go on a little side trip with this equation and work on solving for theta. All right, so here's the equation we just found. And what we want to do here is work towards solving for theta here. But before we explicitly solve for theta, there are some things that we can simplify here in this equation first. And it's not going to initially be obvious, but something that we can manipulate here is this side of the equation right here. The magnitude of vector v minus vector u squared. What we can do with this term is actually rewrite it using the dot product. If you remember from a previous lesson on the dot product, we said that the dot product of a vector with itself is equal to the magnitude of that vector squared, right? So if we have the magnitude of vector v minus vector u squared, that's going to be the same as the dot product of that vector with itself. So that will look like this. We'll have vector v minus vector u multiplied by itself via the dot product. And that's still going to be equal to all of these terms. And now what this is going to allow us to do by rewriting this magnitude squared as a dot product of that vector with itself is now we can use one of the properties of the dot product, in particular the distributive property, which will allow us to multiply vector v minus vector u to each of these vectors individually. Right, so that will look like this. We'll have vector v minus vector u times vector v, and then minus vector v minus vector u times vector u. All right, now just to make sure that you're following, I multiplied this vector of vector v minus vector u by each of these vectors individually. So we have this vector times vector v right here, and then we are subtracting this vector times vector u, which we have right here. All right, and then I'm going to distribute again. I'm going to multiply vector v by both of these vectors and vector u by both of these vectors. And by the way, these terms are still equal to this, But now if we actually work on distributing vector v through this quantity and vector u through this quantity, we'll have vector v times itself via the dot product, and then we'll subtract vector v multiplied by vector u, and then we're subtracting vector u times vector v minus vector u times itself. All right, and that's still equal to all of these terms. All right, now as a recap, we multiplied vector v through this quantity, so vector v times vector v right here. Then we have minus vector v times vector u right here. Then we're subtracting the distribution of vector u through this quantity, so we're subtracting all of those terms. We have vector u times vector v right here, and then we're subtracting vector u times itself. All right, now if we distribute this negative through this quantity, this term will become negative and this term will become positive. So I'm just going to do that real quick. I'm going to erase these parentheses, this negative sign, I'm just going to center that, and then this negative sign will become a plus sign. Okay, and now this is really nice because now what's going to happen is that we have vector v multiplied by itself and vector u multiplied by itself, both of them via the dot product, and we know that that's going to be equal to the magnitude of those vectors squared, right? So really what we have here is the magnitude of vector v squared minus vector v times vector u minus u times vector v, but actually the order in which you write the dot product of vectors doesn't matter. So to make it look more like this term, I'm going to put vector v first. The dot product is commutative, so we can do this. So we'll have vector v times vector u again, and then we'll add vector u multiplied by itself, which we're going to rewrite as the magnitude of vector u squared. All right, and that's still equal to all of these terms. But now what's important to realize is that on both sides of the equation, we have the magnitude of vector u squared here, and the magnitude of vector v squared here and here. So what's going to happen is if we subtract the magnitude of vector u squared and the magnitude of vector v squared from both sides of the equation, they're going to cancel out. We can simply just cross out those terms from both sides of the equation. And then another thing that we can do that's going to simplify nicely is that we can combine these two terms. Now that I reordered the multiplication of vector v and vector u here, these two terms look alike, so we can add them together and have negative 2 times vector v times vector u, and that's going to be equal to negative 2 times the magnitude of vector u times the magnitude of vector v times cosine of theta. And now here's where things get really interesting. Notice that we have a factor of negative 2 on both sides of the equation. If we divide both sides by negative 2, those are going to cancel out, so we don't need those either. And so what we're left with is that vector v times vector u via the dot product is equal to the magnitude of vector u times the magnitude of vector v times cosine theta. So if we want to solve for theta, what we should do is first solve for cosine theta by dividing both sides of the equation by the magnitude of vector u times the magnitude of vector v. And so that will look like this. We'll have cosine of theta is equal to vector v multiplied by vector u via the dot product divided by the magnitude of vector v times the magnitude of vector u. Right? We just divided both sides of the equation by these two magnitudes, and so now we're just left with cosine theta is equal to the dot product of vector v and vector u divided by their magnitudes multiplied together. All right, and this equation right here is the equation that we've been working towards this entire video. We now know what cosine of theta is equal to, and so if we want to know what the angle theta is, we just have to use the inverse cosine function, or arc cosine, on both sides of the equation, and we'll have the angle theta, which is the angle between vectors v and u. Okay, and so if you wanted to write it like that, you could. You could also write it like this. The angle theta is equal to arc cosine, or the inverse cosine function of the dot product of vector v and vector u divided by their magnitudes multiplied together. So you have the magnitude of vector v and the magnitude of vector u. That's another way that we could represent the same equation. Okay, but you're more commonly going to see it written like this because this is a nicer way to remember it. Cosine theta is equal to the dot product of v and u divided by their magnitudes. Okay, and so to summarize, if you want to find the angle between two vectors, this is the formula that you want to know. And it's actually not too bad of a formula to remember, because if theta, the angle in question here, is the angle between two vectors, vector v and vector u, it's equal to the dot product of those vectors divided by the magnitude of those vectors multiplied together. All right, so the two vectors in question that the angle that you're trying to find lies between, you just multiply those vectors together via the dot product and divide by each of their magnitudes multiplied together. All right, and then of course you would need to use the inverse cosine function to actually solve for theta, and once you do that, you will find that that angle will be between 0 and pi radians. Or in degrees, that would be between 0 and 180 degrees. Okay, and this formula will work for vectors in both 2 dimensions and 3 dimensions. All right, so it doesn't matter how many dimensions you're working with, this is the formula that you can use to find the angle between two vectors. Okay, but now if we return to our work, there's one more thing that I want to point out here that's interesting about this formula. If you look back to the second to last equation in our work, where we cancel out these negative 2's, if I erase those negative 2's, look at the equation that we have here. We have the dot product of vector v and vector u is equal to the magnitude of vector u times the magnitude of vector v times cosine theta. This is actually another significant equation that results from the use of the law of cosines. What we have here is another definition of the dot product. Sometimes you'll hear this called the alternate form of the dot product, which you can use when you know the angle between the two vectors that you're multiplying together. Right, so if you wanted to find the dot product between two vectors whose components you don't know, but you do know their magnitude and the angle between them, this is a way that you could find that dot product. Okay, because remember, traditionally, the dot product is equal to the sum of the product of corresponding components. So you would have v1 times u1, and then you'd add that to v2 times u2. And if you had 3D vectors, then you would also add that to v3 times u3. That's the traditional way of calculating the dot product. But if you don't know those components, right, v1, u1, v2, u2, v3, and u3 are the corresponding components of vector v and vector u. If you didn't know those components, but for some reason you know the magnitude of those vectors and the angle between them, this is another way that you could calculate the dot product for those vectors. All right, and so I want to make a note of this. Let's summarize this formula. We now have an alternate form of the dot product, where if we want to find the dot product between two vectors, vector v and vector u, we can find it by taking the magnitude of vector v, multiplying it by the magnitude of vector u, and then multiplying that by cosine of theta, where theta is the angle between those two vectors. And once again, that angle should be between 0 and pi radians, or in degrees between 0 and 180 degrees. Okay, but now once again, let's go back to our work here, because there is actually something interesting that we can learn from this alternate form of the dot product. If I clean up my work a little bit here, if we let our angle theta be equal to pi divided by 2 radians, which is the same as 90 degrees, by the way. In other words, if our two vectors, vector v and vector u, this is vector v and this is vector u, if the angle between them is a right angle, which is pi divided by 2 radians, or 90 degrees, watch what happens to the dot product of those two vectors. It's going to be equal to their magnitudes multiplied together. So we have the magnitude of vector u and the magnitude of vector v. And by the way, it doesn't matter the order in which you write those two. You could have the magnitude of vector v first and then the magnitude of vector u. It doesn't matter because multiplication is commutative. But anyway, you're then going to have cosine of the angle, which is pi divided by 2. So we have cosine of pi divided by 2, and cosine of pi divided by 2 is 0, right? So this would be equal to those magnitudes, the magnitude of vector u times the magnitude of vector v, and then you'd be multiplying by 0, which makes everything 0, and so the dot product of vector v and vector u is 0 when the angle between those two vectors is 90 degrees, or pi divided by 2. Okay, and this is actually very significant because what this tells us is that if you take the dot product of two vectors and you get 0, that means that your vectors are perpendicular. They make an angle of 90 degrees with each other. And sometimes in Calculus 3, you'll hear that referred to as the vectors being orthogonal. And in case you haven't seen that word before, it looks like this, orthogonal. It means the same thing as being perpendicular. But if two vectors are perpendicular or orthogonal, this is the only way it's going to happen. If the angle between those two vectors is pi divided by 2 radians, or 90 degrees. All right. When the dot product of those vectors is 0, the vectors will be perpendicular. Okay, and so that makes for a nice check. If you're ever asked if two vectors are perpendicular, you can just quick take the dot product of those vectors. You don't even have to use this definition. You can use the traditional definition. And if that dot product is equal to 0, then you know that the vectors are perpendicular or orthogonal. But if it's not equal to 0, then you know that the vectors are not perpendicular. Okay, so just make a note of that here, that when the dot product of a vector and another vector, such as vector v and vector u, when that is equal to 0, that is the definition of perpendicular or orthogonal vectors. Okay, so just be sure to make a note of that. But now one more thing regarding the dot product between two vectors. We can actually use the result of the dot product even when it's not 0 to help us determine what type of angle is between vector v and vector u. And so let me show you what I mean. Here I have some rules for the dot product as it relates to the angle between two vectors. And this looks like a lot of information to take in at first, but it's actually not too bad. Let's break it down. This first one here doesn't involve the dot product, but it is good to know when you have two vectors, vector v and vector u, and they're pointing in opposite directions and they're parallel, the angle between those vectors will be pi. Or in degrees, that's 180 degrees. Right, so as you can see here, vector v and vector u are parallel, but they're pointing in opposite directions, so the angle between those two vectors is 180 degrees, or an angle of pi radians. And of course, when theta is equal to pi, or 180 degrees, cosine theta is equal to -1. Okay, so if you know that the angle between two vectors is pi, then you know that they're parallel and they're pointing in opposite directions. Now next up, we are working with a dot product here. If you have a dot product of two vectors, vector v and vector u, and the result is less than 0, then the angle between those two vectors is an obtuse angle, meaning it's between pi divided by 2 and pi radians. Or in degrees, that means it's between 90 degrees and 180 degrees. And of course, when you're working with those angles, cosine theta is between -1 and 0. All right, so the angle between vector v and vector u will be an obtuse angle when the dot product of those vectors is less than 0. That angle will be bigger than 90 degrees, but it will be less than 180. All right, then next up we have what we just talked about with our vectors being perpendicular or orthogonal. When the dot product is equal to 0, we know for a fact that those two vectors are perpendicular. That's at the angle of pi divided by 2, where cosine theta is equal to 0. All right, so that's the definition of perpendicular vectors. But then over here, we have that if the dot product of two vectors is greater than 0, then the angle between those two vectors is acute. In other words, the angle is between 0 and pi divided by 2 radians, or in degrees, that's between 0 and 90. All right, and so when you're working with those angles, cosine theta is between 0 and +1. And so that angle between vector v and vector u will be an acute angle when the dot product is greater than 0. All right, the angle between those two vectors will be less than 90 degrees, or pi divided by 2 radians, but greater than 0. All right, and then finally, if your two vectors are parallel, but are in the same direction, right, not the opposite direction, but the same direction, then the angle between those two vectors must be 0. And of course, when the angle is 0, cosine of theta is equal to 1. And so you can see that here, vector u and vector v are parallel and pointing in the same direction, so they're right on top of each other, so the angle between those two vectors is clearly 0. There is no angle between those two vectors. They're in the same direction and they're parallel. All right, so if you know that the angle between two vectors is 0, you can also conclude that they're parallel, just like if the angle is pi. The only difference is that when the angle is pi, the vectors are pointing in the opposite direction, but when the angle is 0, they're pointing in the same direction. Okay, and by the way, you might have noticed that when we measure the angle between two vectors, that angle is never bigger than pi, or 180 degrees. And there is a reason for that, because when we measure the angle between two vectors, we always want to measure the smallest angle. And here's what I mean by that. The biggest angle that we can have between vector u and vector v will be 180 degrees, or an angle of pi radians. If we were to try to make a bigger angle, right, if we're looking at this example right here, if we were to keep vector v right here, but pivot vector u downward, right? So if we made vector u look something like this, sure, the angle from vector v this way to vector u is now bigger than 180 degrees, but we don't look at that angle. That's not the angle we're interested in. We are interested in the smaller angle between vector v and vector u. So we would measure this angle right here, which is going to be smaller than 180 degrees. All right, so we always measure the smaller angle, and so that's why the angle between our two vectors will always be between 0 and 180 degrees, or pi radians. All right, because once you pass that angle, you can just measure a shorter angle in the other direction. Okay, so those are just some rules that you want to know in terms of the dot product and how it relates to the angle between two vectors. But now before we look at some example problems of using the formulas that we've looked at in this video, I want to quickly talk about one more thing relating to our standard unit vectors. All right, so I have a quick note here that I want to go over. For our standard unit vectors, I, j, and k, where I is a standard unit vector in the x direction, j is a standard unit vector in the y direction, and k is a standard unit vector in the z direction, what do you think is going to happen if we were to multiply these vectors by each other using the dot product, right? Now that we know that the dot product can give us an idea of what type of angle is between our vectors, what do you think the result will be of I times j, or I times k, or j times k? Well, if you think about our 3D coordinate system, where we have an x-axis, a y-axis, and a z-axis, right? This is the z, this is the x, and this is the y. Each of those axes are perpendicular to each other, right? The z-axis is perpendicular to both the x and y, the y-axis is perpendicular to both the z and x, and the x-axis is perpendicular to both the y and z. Since we know that is true, and each of these standard unit vectors represent each of these directions, the x direction, y direction, and z direction, then it makes sense that the dot product between each of these vectors with each other should be 0. Because when the dot product between two vectors is 0, they are perpendicular. That's what we were just talking about earlier in this lesson. All right, so if this is vector I, this is vector j, and this is vector k, then we can see visually from this 3D coordinate system that each of those standard unit vectors are perpendicular. And I guess I should write this as well, that they reach out to a value of 1 in their respective directions. But anyway, we can now conclude that vector I times vector j via the dot product will be equal to 0. We can also conclude that vector I times vector k would also be equal to 0. And we can conclude that vector j times vector k is equal to 0. All right, we know that this is true because all three of these vectors are mutually orthogonal, or they're all perpendicular to each other, right? The phrase mutually orthogonal is just a fancy way to say that all three of these unit vectors are perpendicular to each other. All right, and so because of that, the dot product of those vectors with each other will be 0. Okay, and so maybe you want to make a note of that as well if you're taking notes. I would just write down that we now know that vectors I, j, and k are mutually orthogonal. And once again, that just means that they're all perpendicular to each other. But this is the formal way of saying that. Okay, and so that's all I wanted to talk about in terms of our standard unit vectors. But now let's actually take a look at some examples where we use the various formulas that we found and talked about in this video. Hey there, real quick, before we get to the next part of this lesson, if you find my tutorial videos here at JK Math to be helpful and you want access to more content such as exclusive bonus videos and dark mode versions of my videos, I'd invite you to check out my membership site JK Math Plus, where all of that content is available. To learn how to join and see a full list of everything you'd get access to as a member, you can head over to jkmathematics.com/plus. I'll have a link for that in the description of this video. Okay, so if you're interested in becoming a member, feel free to check that out. It's a great way to support me and the tutorials I make, as well as a great way for you to learn math better. But for now, let's get back to the lesson. All right, so here's our first example. We want to find the angle between vector v, which is the position vector of the point 1, 1, 1, and vector u, which is equal to 2i plus j minus k. All right, and we're going to be using this formula right here that we found in this video. that cosine of theta is equal to the dot product of vector v and vector u divided by the product of their magnitudes. And of course, theta is the angle between vector v and vector u. All right, and so in order to set up this equation, we're going to need a couple things. We're going to need to know the dot product of vector v and vector u, and we're going to need to know the magnitude of each of those vectors. And so let's start with the magnitudes. Let's find those first. Let's calculate the magnitude of vector v. That's going to be equal to the square root of the sum of the components squared. So we'll have 1 squared plus 1 squared plus 1 squared, right? All the components are 1, so that's pretty easy. 1 squared is 1, so we have 1 plus 1 plus 1. So this is going to be equal to the square root of 3. All right, now for vector u, the magnitude of vector u will be equal to the square root of the sum of its components squared, which in this case, vector u is in the standard unit vector form. So the components are just going to be the coefficients of I, j, and k. So that's 2, and then 1, and negative 1. And just to make sure that you see what I'm talking about, vector u could also be rewritten like this. We would have 2, 1, negative 1. The components of vector u are the coefficients of I, j, and k. So we have 2, 1, and negative 1. But now if we take the sum of those components squared and put them under the square root, we'll have 2 squared plus 1 squared plus negative 1 squared. Now 2 squared is 4, and 1 and negative 1 squared are both 1. So this is equal to the square root of 4 plus 1, which is going to be 6. So this is equal to the square root of 6. Okay, so now we have the magnitude of v and u. Now what we want to find is the dot product of vector v and vector u. So let's do that. We'll have vector v times vector u. And remember, the dot product is equal to the sum of the product of the corresponding components. So we're going to find the product of the x components, then add that to the product of the y components, and then add that to the product of the z components. So we'll have 1 times 2, which is 2. So we'll have 2 plus 1 times 1, which is 1. So we have 2 plus 1. And then we'll add that to 1 times negative 1, which is negative 1. 1 and negative 1 will cancel out, and so that leaves us with a dot product of 2. Okay, and so now, if we want to find the angle between these two vectors, we have everything that we need to set up this equation. So we'll have cosine of theta is equal to the dot product of v and u, which we have right here, it's 2. So we'll have 2, and that's divided by the magnitudes of those vectors multiplied together. So we'll have the square root of 3 times the square root of 6. All right, so I'll write the square root of 3 times the square root of 6. Now, if we simplify this, the square root of 3 times the square root of 6 will be the square root of 18. So we'll have cosine of theta is equal to 2 divided by the square root of 18. And I'm not going to worry about simplifying that at all, because now what we want to do is solve for theta, which we can do by using the inverse cosine function, which sometimes I'll call arc cosine. So if we continue our work up here, we'll have that theta is equal to arc cosine of 2 divided by the square root of 18, or the inverse cosine function of 2 divided by the square root of 18, right? Using the arc cosine function or the inverse cosine function on both sides of the equation will allow us to solve for theta, because an inverse trig function and a regular trig function will cancel each other out. All right, arc cosine and cosine cancel each other out, so we're left with theta. And now all that's left to do is plug this into your calculator, and you will find that theta is equal to 1.08 radians, or if you convert that into degrees, theta will be equal to 61.9 degrees. All right, so it's up to you which one of those answers you want to use. I typically like to give both unless it's specifically specified which units the problem is looking for. In this case, it's not specified, so I gave both radians and degrees. All right, and maybe you want to indicate that these are the same answer but in different units by just writing or, okay? And if you're not sure how to convert from radians to degrees, for one thing, you could just change what mode your calculator is in, so that it gives this answer to you in radians, and then you can switch it to give it to you in degrees. Or if you would rather just keep it in one mode and convert, I would recommend that you keep it in radians and then convert to degrees. And if you want to do that, remember that if you have an angle in radians, To get that into degrees, you want to multiply by 180 divided by pi. That will give you an angle in degrees. Okay? But with that, we have now found the angle between these two vectors. The angle between vector v and vector u is 61.9 degrees, or 1.08 radians. Let's take a look at another example. All right, so next up we have this example. If the magnitude of vector v is equal to 8, the magnitude of vector w is equal to 5, and the angle between vector v and vector w is pi divided by 3 radians, find the dot product of vector v and vector w. All right, now this example is going to require a different formula, and you can see I have it right down here. This is our alternate form of the dot product, which allows us to find a dot product between two vectors if we know the angle between the two vectors and the magnitude of those vectors. All right, and in this case, we do know all of that information. The angle between vector v and vector w is pi divided by 3, and we're given the magnitudes of vector v and vector w. So in this case, we can use this formula, just replace vector u and its magnitude with vector w and its magnitude. So here's what we'll have. We'll have vector v times vector w, via the dot product, will be equal to the magnitude of vector v times the magnitude of vector w times cosine of theta. And I'm going to use a different color for theta here, and so I'll write it like that. Okay? Now we know that theta is equal to pi divided by 3, and then the magnitudes that we need are right here. So we can just plug everything in here to find our dot product. So this will be equal to the magnitude of vector v, which is 8. So we'll have 8 times the magnitude of vector w, which is 5. So we'll have 5, and then we're multiplying by cosine of the angle, which is pi divided by 3. Okay, now 8 times 5 is 40. So this is equal to 40 times cosine of pi divided by 3. And maybe you know this by memory. If not, just plug it into your calculator. Cosine of pi divided by 3 is equal to 1/2. All right, and then 40 times 1/2 is equal to 20. And so 20 is the dot product of vector v and vector w. We don't know what the components of vector v and vector w are, so we couldn't calculate the dot product the normal way, but we could use this alternate form that allows us to find the dot product if we know the magnitude of those vectors and the angle between them. Okay? So that was just an example of how you can use this alternate form of the dot product. But now let's take a look at one more example for this video that relates to the angle between two vectors. All right, so for this example, we want to determine if vector A, which is the position vector of the point 2, -1, 5, and vector B, which is equal to 2/5 I minus 1/5 j plus k, are perpendicular, parallel, or neither. All right, now this is really going to test our knowledge of vectors, and if we understand what it means for two vectors to be perpendicular or parallel. All right, or potentially neither as well. You should be able to determine if they're neither, given what needs to be true in order for them to be perpendicular or parallel. All right, and let's get the easiest one out of the way. Remember that the definition of perpendicular vectors is if the dot product of those vectors is 0. So let's see if that's true. Let's calculate the dot product between vector A and vector B, and if it's 0, then we can determine that they're perpendicular. All right, so we'll have vector A times vector B, and the dot product will be equal to the sum of the product of their corresponding components. And just to make it more clear what vector b is, I'm just going to rewrite it here in the standard form. Vector b is equal to 2/5, comma, -1/5, comma 1, right? We're just taking the coefficients of I, j, and k that makes up the components of our vector. And now let's work on the dot product. We'll start by multiplying the x components together. So we have 2 times 2/5, which will give us 4/5. Then we'll add that to the product of the y components. -1 times -1/5 will be +1/5. And then we'll add that to the product of the z components. So we have 5 times 1, which is 5. All right, now this is equal to 4/5 plus 1/5, which is 5/5, which is just the same as 1. So we have 1 plus 5, which is equal to 6. And 6, obviously, is not equal to 0. And so we can conclude that these two vectors are not perpendicular. All right, so we can say not perpendicular. In order for vector A and vector B to be perpendicular or orthogonal, the dot product of those vectors needs to be 0. In this case, it's not. It's 6. Okay, so we know they're not perpendicular, but are these two vectors parallel? Well, the easiest way that we can check that for vectors in 3D is to see if we can show that they are scalar multiples. Now, if you struggle with figuring out if two vectors are scalar multiples, you could also find a unit vector in the same direction as one of them, and then see if the other vector has the same unit vector, but that's a little bit of extra work that I don't want to do in this case. And if you're not familiar with what I'm talking about, be sure to check out my lesson on unit vectors. But what I'm going to do here is just look at vector B and see if I can show that it is a scalar multiple of vector A. All right, so I'm going to see if there's some type of scalar value that I can pull out of each of these components and get a vector that looks like vector A. And in this case, it actually looks like we can do that. All right, let me show you what I mean. If vector B is equal to 2/5, -1/5, 1, notice that these first two components are being divided by 5, right? We have 2/5 and -1/5. And so what I'm tempted to do here is pull out a factor of 1/5 from each of these components, and that's actually going to work out pretty nicely. Watch what happens here. This will be equal to 1/5 times 2, -1, and then what is 1 divided by 1/5? If you pull out 1/5 out of 1, what do you get? Well, I'll just do a little bit of side work here. If we have 1 and we're dividing by 1/5, that's the same as multiplying by the reciprocal of that fraction. So we have 1 times 5 divided by 1. And so that's just going to be equal to 5. All right, so 1 divided by 1/5 is 5. So our last component is 5. And look at this vector. We have 2, -1, 5, the same exact vector as vector A. So we can conclude that vector B is equal to 1/5 times vector A. And so since vector B is a scalar multiple of vector A, or really you could say that both vectors are scalar multiples of each other, then we can conclude that these two vectors are parallel. So I'm going to circle parallel here, but if you want to write out a more formal answer, you can conclude here that vector A is parallel to vector B. All right, writing two lines like that is a way to write parallel. All right, vector A is parallel to vector B. Okay, and so that's it for this example. We have now determined if these two vectors were perpendicular, parallel, or neither, and we found that they weren't perpendicular, but they were parallel. And so with that, that's it for this example, and this was the last example for this video. But if you want to see some more examples, feel free to check out my examples video that I'll have linked here on the screen. If you have any questions, feel free to leave those in the comments. But if you don't have any questions, this is all I had for now. So I will see you next time.